This is for 6.1, 6.2. We're going to look at distribution of continuous random variables and density graphs to start with. What we're going to look at here is different than our previous section where we looked at discrete random variables. Now we're going to look at variables that are continuous, right? And unlike discrete variable, right, we cannot list out all the possible outcomes of a continuous random variable. And so looking at that beginning piece right here, instead we use what's called a density curve to represent all the possible outcomes. And so before we continue, recall please what a distribution is, right? It's all the possible values. And the second part is the frequency or probability or proportion of those values. And so again, important here is that the variable we're investigating is continuous versus being discrete. Discrete has a list, a certain amount of outcomes, a finite amount in most cases. Continuous, again, is this idea that I cannot list out all the possible outcomes, right? And so we'll take a look at some examples so you get a better idea what we mean by continuous. And so in a continuous random variable, we look at the curve, something like this, these normal distributions, which we're going to focus on. Those are called density curves, right? And on those curves, the x-axis represents the possible outcomes, the y-axis represents the density at each point in the distribution, right? And most importantly, the area underneath the curve of a density curve, right? We don't calculate it using mathematical like geometry. We use technology to help us calculate that, the area underneath the curve, because what that represents, right? It represents the probability or the proportion or the relative frequency of observing an event or an outcome within that interval, right? So we're going to remember, we'll be talking about the word area, but when we talk about that word area, what we're really talking about is probability. And so important properties of a density curve, right? They're always positive, right? There's no negative because we're talking about probabilities, and the total area equals 1 because of 100%. When we're talking about probabilities, the largest value we can have. And this goes back to, we started talking about mean and standard deviation with normal distributions. And so when we collect data in the world, much of the data we collect follows a normal distribution where you have a mean in the middle, and then you have and then we mark it off by the number of standard deviations so we can kind of measure ourselves, which we do with z-scores. And so we have these z-scores here. So we got to remember what a z-score is. If the x values are normally distributed, then their z-scores will follow this distribution, right? Meaning that most people will be within 1 standard deviation, which is 68%. Most of the data would be within 2 standard deviations, either 2 above or 2 below, 95% of the data. And so is 99.7% of the data is within 3 standard deviations. Important is that these numbers are pretty much estimates, very close estimates. If you do the actual calculations, these numbers are a little bit off, but these are our estimates for now, for the time being, so that we can utilize probabilities with data. And the last thing is, you might see this notation n0, 1. This means that whatever data we're looking at is normally distributed, the mean is 0, and the standard deviation is 1. We'll see that notation a little bit